Welcome to today's video where I'm going to show you something called the binomial theorem. This is a bit of a change of pace from what we've been working on in regard to polynomials. This is going to now look at how to expand binomials. We're going to look at doing this through two different strategies. First one will be Pascal's Triangle, and the second one will be using what are called combinations. Now, before we can get into this using Pascal's Triangle, well, we have to make sure you know what Pascal's Triangle is. So, let's have a look down here below. I think I have a picture of it. So this is a picture of what Pascal's Triangle, sorry. Here we go. So here's a look at Pascal's Triangle. So Pascal's Triangle is named after a famous mathematician. Last name Pascal. Can't remember, there was a few Pascals, but anyway, it goes by the pattern that you see down below here. Now, we need to see if we can identify how this pattern works so that we could make more rows of this triangle if we needed. So if you looked at this pattern, it goes 1, 1, 1, 1, 2, 1. Well, it clearly starts with a 1, ends with a 1, starts with a 1, ends with a 1. Now, every successive row is found kind of like this pyramid effect where you look at the two numbers above and you add them. 4 and 6, 10. 6 and 4, 10. 4 and 1, 5 and 1. Next row would be 1, 6, 15, 20, 15, 6, and 1. Make sure you always put the sum of these two in between them, and that will give you that triangle effect as this goes on. And this triangle goes forever. As I said, it's referred to as Pascal's Triangle. It has all kinds of neat patterns in it. The one we're going to use it to help us with is expanding binomials, and he developed what's called the binomial theorem. Whoops. Now, before I get to the binomial theorem, one of the biggest misconceptions students have in mathematics is if they have something like x plus 2 to the 4th power, you would be, maybe you wouldn't be, but there's far, far too many people who think that this just equals x to the 4th plus 2 to the power of 4 equals that. That is incorrect. You should know already, just from doing one like x plus 3 squared, so this is a binomial squared, that x squared plus 6x plus 9 is the correct version. I didn't just square this one and square this one. In math, there's always something we refer to as a counterexample. If I took this one and I wanted to show you that this doesn't work, just use numbers. If I put in here 2, let's use easy numbers, 2 plus 1 to the 4th power. Well, if I want to get the value of this, 2 plus 1 is, you have to do inside the bracket first, then raise it to the 4th power. I know that the correct answer is 81. Well, if I do like some of students want to do here, by just raising each of these to the 4th power, 2 to the 4th power is 16, 1 to the 4th power is 1, you would want to tell me that the answer is 17, which is incorrect. So there's a counterexample to show you why you can't just raise each of these to the 4th power. What this really means is the binomial x plus 2 multiplied by itself 4 times. Well, you can imagine if you expand that out, that's going to involve quite a bit of work, and there's going to certainly be more than just these two terms here if you expand that all out. What I'm going to show you is a shortcut called the binomial theorem. And as I said, first time we're going to do this, we're going to use Pascal's Triangle. Well, I'm going to write down here x squared plus 2xy squared. There's going to be a pattern here that I'm going to show you. This is x cubed, sorry, plus 3x squared y plus 3xy squared plus y to the third. X to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Now, so this right here, if I took x plus y and squared it, I would get x squared plus 2xy plus 1y squared. 1, 2, 1. Notice the pattern. If I took x plus y, now I know the pattern, so you may be wondering, how the heck do you write those out so quick? I know this pattern, how it works. X plus y cubed is 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. 1, 3, 3, 1. Look at that, those four numbers. X plus y to the fourth power is 1x to the fourth plus 4x cubed plus, or 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the fourth. 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. So these coefficients coincide with the row of Pascal's triangle, that the second number in the pattern, in the row, will coincide with your exponent up here. So if I'm raising this to the fourth power, my second number in is going to be a 4. If I'm raising something to the fifth power, my second term in would be the fifth power, or it would be a 5, sorry. Now, the problem with this theorem is that if I needed x plus y to the 25th power, well, I'm going to need this triangle. It's not even going to fit on a piece of paper. It would be so wide. As this keeps going, you would need the second row in to be a 25. Well, you can see how this works. It goes up by 1 each time. 1, 2, 3, 4, 5, 6. So you're going to need 19 more rows of this pattern before you're going to hit 25. And the triangle's going to get really, really big. We do have another way to manage it. Regardless of which way you pick, it's a lot of work to expand out a binomial to the 25th power, because it means this multiplied by itself 25. This would probably be the least efficient way. Well, multiplying it out longhand would be the least efficient way. Pascal's triangle would be the second least efficient way. And the best way to do this one would be our second method we're going to show you in the next video, called using combinations. Now, I've looked at x plus y to the fourth already. Let's look at x plus y to the fifth, just because we've already done to the fourth. You can see it right up there. So if I was going to do x plus y to the fifth, it would be 1 x y plus 5 x y plus 10 x y plus 5 x y plus 1 x y. Now, the pattern of the binomial theorem, your coefficients, I believe everyone sees hopefully where they came from. Because it was to the fifth power, I knew I was using this row. These became my coefficients. This is a really easy example because the first term in the binomial is x and the second term in the binomial is a plus y. The theorem in general, though, if this had been, let's say, x to the third and y to the fourth, or even 2y to the fourth, well, then I would have been filling in here x to the third and 2y to the fourth. Inside of these brackets in the pattern will always be the two terms of your binomial. Now let's get rid of those. Go back to the way we were. Now I don't know if anyone noticed the pattern up here. Let's look at to the fourth. My exponents went 4. Well, there was no y there. Well, there really was, but it was y to the 0. Then it was x to the 3 and y was to the 1. X was to the 2 and y was to the 2. x was to the 1 and y was to the 3. And they say, oh, there's no x. Well, there really was. It was x to the 0. Now, notice what happened here as we went from term to term. The power of x, or the first term in this case of my binomial, it went down. It was 4, then it was 3, then it was 2, and then it was 1, and then it was 0. Versus the second term started at 0, and it worked its way up. It was 0, it was 1, it was 2, it was 3, and then it was 4. Well, if I put that into play here now then, these exponents should start out 5 and 0, 4 and 1, 3 and 2, 2 and 3. What did I screw up? 5, 4, 3, 2. I missed a term here. Oh, there was 2 10s. Just give me a second to fix this. Okay, there, I fixed. So I was missing. I went 1, 5, 10. I jumped the 10. I didn't use it. You were probably noticing that, hopefully. So now I've got 1, 5, 10, 10, 5, 1. My exponents are going 5, 4, 3, 2, 1, 0. Now the beauty of me picking up on my error there was that I knew how the pattern was supposed to work, and it wasn't working because I wasn't hitting 0 here. So then I was able to figure out, oh, okay, I see I'm missing a term. That's the nice thing about when you eventually get to the point where you understand the pattern, you might be able to pick up on a careless mistake, something like that. So then I went 0, 1, 2. This one should be to the 3, 4, and 5, and that's how it should work. It should start out 5 and 0. Now I want you to notice something else. In this first term in my binomial expansion, using the binomial theorem, because it's to the 5th power, my exponents were 5 and 0, they add up to 5. 4 and 1, they add up to 5. 3 and 2, they add up to 5. 2 and 3, 1 and 4, 0 and 5. Your exponents in the pattern here will always add up to this exponent. That'll be important, especially later on when we just start picking out a single term to find. All right, so now we're not going to stop at this. We're going to tidy it up and make it look more like a polynomial that we're used to seeing. So it would be x to the 5th, because that's a 1, plus 5, x to the 4, y, we don't have to put a 1 on it, plus 10, x cubed, y squared, plus 10, x squared, y cubed, plus 5x, y to the 4th, 1, 1, leaving me with y to the 5th. There is the binomial x plus y raised to the 5th power. All right, let's take the theorem and put it in play with different binomials. Now, I've got 2x minus 3 to the 3rd power. So I'm going to need 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This is the one I need because it's to the 3rd power. So my second term in is a 3. And it would go like so. So it's 1, 2x this time, because that's the first term in the binomial. And you have to include this sign. Negative 3 will be my second. Plus, I'm just going to put the exponents on at the end. So then 3, 2x, negative 3. Plus 3, 2x, and negative 3. And then plus a 1, 2x, and negative 3. Now I'll put my exponents on. So these 1, 3, 3, 1 came from here. Now I'm going to put my exponents. So if it starts at a 3, the first term in the binomial will start at exponent 3. The second one will be at 0. This will go down 1. This will go up 1. This will go down 1. This will go up 1. This will go down 1. This will go up 1. Now, when I tidy this up, now, very rarely do students not pick up the pattern. I mean, unless they're completely not paying attention or not trying. The pattern to set this up becomes pretty much systematic. The place where students go wrong is expanding this out to write this, which has nothing to do with pre-calc 12a, it's laws of exponents. You have to make sure, for example, when you have something like this, it's 2 cubed and x cubed. So this is 2 cubed is 8. X cubed would be x to the 3rd. Negative 3 to the 0 is 1, and that's 1, so they multiply together to give you just a 1. Now you got to watch here. You've got a 3 out in front, 2 squared, that's a 4, and then a negative 3 to the first power, that's a negative 3. So I always do my numerical coefficients first. So 3 times 2 squared times negative 3 to the 1, that's going to give me negative 12. There's my number in front. X will be squared. There's no other variable in this one. So I've got a 3. You can do this. You don't have to do it writing it up here. If you have a calculator, that especially that has on-screen typing, just type in 3 times 2 to the 1 times negative, make sure you put it in brackets, negative 3 in brackets squared. 3 times 2 is 6. This would be in positive 9. This should be a plus 54. X will be to the 1. This is 1. This whole bracket's a 1 because it's all to the 0, so I just need to do negative 3 to the third. There would be the binomial theorem. Let's grab this one and put it on a new page. All right, so if I go here, now I need the 5th row of Pascal's triangle. I'll just write that out over here. So I've got 1, 1, 2, 1, 1, 3, 3, 1. If you just have the triangle, you don't have to write it out. It's not part of the question. I don't mark Pascal's triangle. So if you just have Pascal's triangle, written out down to the 6th or 7th row, and you just have it sitting in front of you on a sheet, that's fine. You don't have to keep writing it out over and over every question. All right, so I know I'm here because the second number in is a 5, and my exponent here is a 5. Let's get our pattern rolling. So it's a 1. First term in the binomial is 3x squared. The second term in this binomial is negative 5y. I'll leave the exponents for a second. Then I got a 5. 3x squared, negative 5y. A 10. 3x squared, negative 5y. Another 10, didn't forget it this time. Running out of room. Plus, come down here, 5, 3x squared, negative 5y. Maybe I should move that over. Maybe it'll let me compress it down. There we go. One more, so plus a 1, 3x squared, negative 5y. Exponents. Because it's to the 5th power, we start out 5 and 0. Remember, the first one decreases, the other one increases by 1 each time. 3 and 2, 2 and 3, 1 and 4, 0 and 5. As a little check, you can always, again, these two always have to add up to that exponent. If this was a 7, for example, this would have to be like 5 and 2, 4 and 3, 3 and 4, 6 and 1, 1 and 6. They have to combine to give you that exponent. Now, this one's going to be a little bit more work to expand out. So you're probably going to want to grab a calculator to do this one. And because I have to do, I got a 1, but I've got 3 to the 5th. 3 to the 5th is 243, I believe. That's 243. And then this all to the 0 would be a 1. So my first term is going to be 243 x squared, but then it's raised to the 5th. Laws of exponents says when you have an exponent and you raise it to another exponent, you multiply those together. That one's done. Now I've got a 5 times 3 to the 4th power. Now it's a positive, so I don't have to worry too much, but it's in brackets. And then I've got a negative 5 in brackets to the 1st power. As I said, you can be typing this all in your calculator at once. You don't have to write it up here. This would be positive 81 times 5, so 81 times 5. Multiply that then by negative 5. And that's going to give me did I do there? 81 times 5 equals, and then times that by negative 5. Negative 2025 is my second term. X will be to the 4 times 2, 8. And y now will be to the 1 times 1, so just y. That one's done. 10 times 3 to the 3rd power. Negative 5 squared would be a plus 25. 10 multiplied by 27 multiplied by 25. 6,750. It'll be positive this time. The reason it's positive because 3 cubed was positive. Where am I at here? Yeah, 3 cubed was positive, but negative 5 in brackets squared is also positive. And then you have your 10, so it's 3 positive numbers. X would be to the 2 times 3, 6. Y would be to the 1 times 2, y squared. So we got a 10 again. 3 squared would be 9. Negative 5 in brackets to the 3rd power is a negative 125. 10 times 9 times negative 125 is equal to negative 11,250. X will be to the 4, and y will be to the 1 times 3. Will be to the 3. Down here, we've got 5, 3 to the 1, that's 3. Negative 5 in brackets to the 4th power is a positive 625. 625 times 50, 9,375. X will be to the 2, y will be to the 4. Last one, we have a 1. 3 to the 0 is also 1. And then we've got negative 5 to the power of 5, so that's going to be, what's 5 to the 5? 3125. So it'll be a negative, because that's an odd exponent, negative 3125. There'll be no x because that's a whole bracket becomes 1, so it'll be y to the 5th. So even though there was different exponents on here, and there's a lot of work to get to this, trust me, that would be far, what we just did, as much space and time as it would have taken, is far less work than you taking x minus, or 3x squared minus 5y, writing it out multiplied by itself 5 times and trying to do that out by hand. Most likely you're going to make a sign error, or there would just be so many terms you'd have to keep track of and collect. So this theorem definitely makes that type of expanding have a nice pattern for us to follow. In terms of patterns, also in your answer there should be a pattern with your variables. Let's look at the x's and make sure that the pattern doesn't deviate. They're at 10, then it goes x to the 8, x to the 6, x to the 4. So I can see that it's going, the x is going down by 2 every time, and it continued that pattern. Perfect. It shouldn't change. The y's, there's no y here. Now there's a y to the 1, 2, 3, 4, 5. Now they won't follow the same pattern, but each of the variables in the expansion of a binomial will follow a particular pattern, whether it's going up by 4s or 3s or 2s, whatever it may be, or in the other case, the other one where it's going down by a certain number. It won't change midway through your expanding. So that'll help you to check and find careless mistakes if you happen to make one. Now there's no particular pattern of these because it's just the product of 3 different numbers, so not much we can do about that. Now, what we want to look at doing is, maybe I don't want you to expand the whole binomial out. I want you to just find a particular term. So for example, this one says find the numerical coefficient, meaning the number in front, of the term that has x to the 4th, y to the 9th as the variable part. Well, if you were to write out the whole, now this is to the 5th, so I'm going to need 1, 1, 1. Let's get my triangle ready again here. Okay, so I'm on this row because it's the fifth power. There's a whole bunch of terms added. There's going to be some number in front. I'm not sure what it is. There's going to be an x squared, and there's going to be a minus 2y cubed. So every term is going to be that, plus, and we'll fill numbers in here. We're just going to figure out which term does this question want me to focus in on, just this one specific term. Well, because I've got an x squared and I want to get an x to the fourth, the only way that can happen is if this was a 2, because then you'd multiply these, you get your 4. To get a 9, and that being a 3, that's got to be a 3. We knew that had to be a 3 before we started anyway, because do you remember, if this is a 5, these two added together have to give me 5. So as soon as I put a 2 there, that had to be a 3. If I put a 1 there, that would have to be a 4. Meaning I can't just randomly pick exponents here to ask you this question. I have to know what's going to happen here. So then you're going to say, well, how do I know which of these numbers I pick? The way you do that is you go over here and say, well, they start out in the pattern. The first one, it would be the 5 and 0. And then what I mean by that is these exponents would be 5 and 0 to start. You say, well, that's not the one I want. I don't want that one. Then this one is 4 and 1. I don't want that one. This one is 3 and 2. I don't want that one. This one is 2 and 3. That's the one I want. I know then that this number has to be that 10 right there, just because I followed the pattern of what happened to these exponents in order for them to get to the point where that's a 2 and a 3. Then, you're not finished. Now we're going to, like we did the last one, we're going to tidy up this term. So I've got a 10 multiplied by the nice thing, this is just 1 squared, so that's 1. Negative 2 to the power of 3 would be a negative 8. 10 times 1 is 10 times negative 8, negative 80, x to the 4th, y to the 9th. There's the answer to their question. What is the numerical coefficient? That's the answer, negative 80. So without doing the whole thing out and then picking out that one term in your answer, it's much quicker to just know the pattern and follow through and get the value that you're looking for. All right, let's try another one of those. So I've got 3x squared minus 2y cubed. This time it's to the 6th, so I'm going to need 1, 1, 1. Again, I should have just had a version of Pascal's triangle that I kept bringing along with me, but I don't. 10, 5, 1, 6, 20, 15, 6, and 1. So this is the row I need. So let's set it up. There's a number in front. I don't know what it is yet. There's going to be 3x squared, and then minus 2y cubed will be the second one, and then there'll be a bunch of terms here. In order for us to get x squared, I'm going to need a 1 here. And for this to become a 15, I'm going to need a 5 here. Double check, see, does that make sense? 1 and 5, 6. It's all good. Okay, so now I've got to figure out which number here we're dealing with. I'm just going to say them as I'm not going to write them out this time. So this would be 6 and 0. I'll write the first one out. 6 and 0, 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5. It's this one right here. You could start at the other end. I should have, when I saw that the bigger number was here, I should have started this way and went here. Either or, you can go in either direction. You know that you start here at 6 and 0. You know at this end you'd start at 0 and 6. So I know it's this one. We now have a 6, 3 to the 1, and negative 2 to the 5th power, which would be a negative 32. I need to know 18 times negative 32. So 18 times negative 32 is a negative 576. X will be squared and y will be to the 15th. So to answer their question, that is what we would call the numerical coefficient. And that is how you expand binomials using Pascal's triangle, and how you can pick out a particular term like this, so you don't have to go through the whole pattern. I would always ask students at this point, Do you think it would be possible to get this question correct if you don't know the binomial theorem and how to integrate Pascal's triangle into expanding a binomial? Absolutely not. So if I can get you to figure out one term, that's a quicker way to get students to show me they know how to do Pascal's triangle. And sorry, the binomial theorem using Pascal's triangle. All right, so that's your first look at how to expand binomials using Pascal's triangle. Hopefully I've shown you enough examples as to how you can expand these out and apply them to make your life a bit easier in terms of expanding binomials. As I said, there is another way to do this, which will follow in a later video. Thanks for watching. If you have any questions or concerns, as always, reach out for some extra help. Take care.